Hello, my name's Clinton and I'll be your guide through this second module of Day 10. We're going to talk some more about the sine function. Please don't forget to pause this presentation at any time if you need a bit more time to think about something. We're now going to look at a whole family of different functions which are based on the sine function that we saw in Module 1. In the same way that y equals x is a linear function, and indeed perhaps the prototypical one, as a straight diagonal line through the origin, but ax plus by plus c equals 0 is the equation of a general linear function, we're going to see that y equals sine x is just one of a family of sine-like functions. What happens when we multiply the sine function by some constant a? Here's the graph of y equals sine x. Here's y equals 2 sine x, y equals 3 sine x, and y equals 4 sine x. The graph of y equals sine x, which we saw in the previous module, is always between minus 1 and 1. However, when we multiply by some constant a, the graph of the new function y equals a sine x is always going to be between a and minus a. This number a is called the amplitude of the function y equals a sine x. The ordinary sine function y equals sine x has amplitude 1. Now let's change a different part of the function and see what happens. Here's the graph of y equals sine x. Here is y equals sine 2x. Notice we're now calculating the sine of 2x rather than 2 times the sine of x. But here is y equals sine x on 2, or half x. And here's sine y equals 3x, for good measure. If we change y equals sine x to y equals sine omega x, that letter which looks a bit like a W is a Greek letter, omega, the effect is to stretch or compress the graph horizontally. If omega is bigger than 1, the effect is to compress the curve. You should imagine we now have to fit the full sine curve in omega times where it previously fit once. We saw this above with omega equals 2 and 3. If omega is less than 1, the effect is to stretch the graph. You should imagine now we have 1 on omega, which is bigger than 1 since omega is less than 1, 1 on omega times as much space to fit a full sine curve. We saw this above with omega equals a half. The number 2 pi divided by omega is called the period of the function y equals sine omega x. The ordinary sine function y equals sine x has period 2 pi, because there omega is 1. The general form of a sine curve is y equals a sine omega x. If we're given such a curve to sketch, we don't need to use calculus. We know the amplitude is a, and the period is 2 pi on omega, and this is enough to draw the curve, since we know what its basic shape is. The amplitude a will determine how high and low on the y-axis the curve goes, and the period, 2 pi on omega, will determine how stretched or compressed it is horizontally. Let's see an example. We want to sketch the curve y equals 2 sine 3x. We can read off that the amplitude is 2, and that the period is 2 pi on 3. This means that the graph repeats itself every 2 pi on 3 units. Here's what the graph looks like. The amplitude and period are drawn in as well. Notice that the amplitude is 2, so the graph is always between 2 and minus 2, and that the whole sine curve fits in between 0 and 2 pi on 3, and repeats itself every 2 pi on 3. Try some of these questions to get practice at sketching general sine curves. Press pause, and then press play when you want to continue. Here are the answers.